Well, hello. Welcome. My name is Gail Mayhood. I'm a professor in the Department of Geological and Environmental Sciences. And it's my pleasure today to introduce and to welcome back to Stanford, Jake Lowenstern. Jake did his undergraduate geology work at Dartmouth, graduating in 1986, and then he spent the following year on a Fulbright scholarship in Sicily, where he got his first introduction to volcanic hazards, including a close escape from a fast-moving lava flow from Etna. He then came to Stanford, where I had the pleasure of working with him as a PhD student, where he worked on the metal and volatile budgets of young rhyolitic eruptions from the 1912 eruption of Valley 10,000 Smokes and a lovely little volcano in the middle of the Mediterranean called Pantelleria. He did that in 1992. And then he spent a year as a postdoc at the Japanese Geological Survey working with Jeff Hedenquist, where he then expanded his work to the origin of hydrothermal ore deposits more generally. Since then, he's worked at the U.S. Geological Survey, where he studies the interactions of magmatic systems and their overlying hydrothermal systems, applying techniques ranging from good old-fashioned fieldwork to chemical and isotopic analyses of gases and fluids to igneous petrology and uranium-lead geochronology. In 2000, he was awarded the Lindgren Award of the Society of Economic Geologists for his groundbreaking work on research that involved analysis of silicate melt inclusions that were trapped in phenocrysts in volcanic rocks, and the significance of these results for understanding the formation of hydrothermal ore deposits for magmatic outgassing and volcanic hazards. This award, which is given out by the mineral deposits community to their young rising stars, is all the more extraordinary because Jake was not trained as a classical ore jock, and yet his research has had an important impact in that field. Shortly after his appointment in 2002 as the scientist in charge of the Yellowstone Volcano Observatory, there was a flurry of seismic and hydrothermal eruptions that plunged him into the next phase of his career, which was essentially dealing with the public. And late in 2003, the BBC decided to produce a 2-hour docudrama on Yellowstone, which they entitled Supervolcano. And it chronicled a sort of near-future catastrophic eruption modeled on the 2-million-year-old eruption that happened there that erupted 2,500 cubic kilometers of magma, spreading ash all across the central part of the U.S., all the way as far as Texas and Southern California. That movie that came out in 2005 was surprisingly accurate, and a lot of that the credit goes to Jake, in that he was a consultant for it. It's also clear that he was also the model for the protagonist of the movie, who actually almost looks a little bit like Jake. He was the scientist in charge of YBO, even down to his name. Jake Lowenstern, the fictional YBO person, was called Rick Lieberman, Lowenstein Lieberman, and he also had 2 little girls in the movie. But I do have to say that Jake has a much better sense of humor than the fictional YBO scientist had. Today, Jake will be talking to us about the Yellowstone supervolcano, past, present, and future. Please join me in welcoming Jake.
Well, thank you very much. I'm delighted to be here. I never really went away for the most part. I come back and work here and visit with people on occasion, but I certainly have never been in this beautiful room and given a talk to as many folks as are here today, so that's great. And while we're kind of a little bit down memory lane, and since it is a Thursday and social media aficionados know that it's Throwback Thursday, so I am going to throw it back to 1989 when I was a third-year graduate student, and there was a little earthquake, prevented me from going home and watching baseball, and I just thought we all kind of stammered out of the building. I had to run out of the geology corner. We sat around and tried to figure out what had just happened, listening to radios or TVs plugged into car batteries, and that was over by the chemistry building. And as Gary Ernst figured out, we weren't going to be back in the geo corner anytime soon. It took 5 years before it got renovated. I had to move out, and I lived my life in Bambi. I think Gary named Godzilla and Bambi for an interesting cartoon. You can find it on YouTube. It's very, very funny. And Bambi, sad to say, I think still exists today, 25 years later. You guys, shame on you for letting that thing go on. Anyway, but I digress. We're here to talk about Yellowstone today. And Yellowstone is many things to many people. Of course, it's our first national park. It's the first national park in our country. It's the first national park in the world. And it's set the stage for our society preserving wild places and special places for the future generations to enjoy. But Yellowstone is also, it was set aside because of its fantastic geothermal features. Its boiling aquifer of groundwater. And it's known, of course, for its spectacular Rocky Mountain scenery, for its great fly fishing, admired for many years, including by this Stanford grad, and for its charismatic megafauna, for which people travel all around the world. Over the past few years, Yellowstone has become more and more known as the supervolcano, and this indeed is from the movie Gail was just referring to. And there's a lot of documentaries. Some of them are good. Most of them are pretty bad. There's a lot of media attention. There's a lot of hyperbole that gets directed towards Yellowstone these days. And so in our the next 45 minutes or so, I want to sort of cut through all that. And let's talk about what really is going on at Yellowstone, what's there, what's happened in the past, what's going on today. And I'm going to focus on geology, geophysics, and geochemistry. I'm going to sort of intersperse the talk with various little bits on recent research in volcanology that relates to the Yellowstone and its current activity. And one overall message I want to give people is that everything happens. Yellowstone's sort of the Texas of volcanoes in some ways. Things that are happening on a big scale there. And things that are happening elsewhere on Earth, sometimes we can't quite figure out whether they're happening or not, but at Yellowstone, you can see, yeah, this really happens. And so it can give us insight into other topics, a lot of topics that we can look at in the Earth environmental sciences. My work at Yellowstone stems through my work with the Yellowstone Volcano Observatory, and that's 8 different agencies. It's a virtual observatory. There's no actual building. We have some storage in Yellowstone, but we have these 8 different organizations. University of Utah and UNAVCO work on the monitoring systems. The USGS runs all the volcano observatories. We have the 3 state geological surveys, the University of Wyoming. So we work together, and so that's just a little bit of background there. Okay, so I'm just going to bring it back right now to sort of why is Yellowstone there in the first place. A lot of you know more about this subject than I do, but there's been volcanic activity for the last 17 million years in the western U.S., starting with the Columbia River basalts in the northern Nevada Rift. And then there's continuing volcanic activity out into Oregon and up through the Snake River Plain towards present-day Yellowstone. Now I'm going to try to give sort of the basics here in that all of these yellow features here, circular features, these are calderas, and they march up towards the northeast, in the opposite direction to the North American Plate movement. And each of these represents a caldera, and the caldera is a large hole in the ground, sort of a cave-in, a sinkhole from a giant volcanic eruption where you take a huge amount of magma, you put it out on the ground surface, and you have the ground surface caves in. You get a caldera. The calderas get progressively younger as we move towards the northeast, and present-day Yellowstone sits right here. There's a lot of recent studies from seismic analysis especially, tomography, looking at the hotspot beneath Yellowstone. Most models for the hotspot these days are plumes, but there's other models as well. There's also other kinds of data, but in general, people find evidence for significant amounts of melting going on beneath the present-day Yellowstone, or very, very hot mantle temperatures, and that's controlling what's happening up at the surface. And here's a diagram that gives a sort of a picture of the way many of us think about what's happening beneath Yellowstone. We have basaltic magma similar to what's happening, what's erupting in Hawaii, and it's forming down in the mantle, and it's rising into the crust. It melts the crust. It also crystallizes. The residual melts mix with the crustal melts. They form a silicic magma reservoir, sometimes called rhyolitic magma, that's found up in the upper part of the crust, 5 to 15 kilometers. And that occasionally erupts, forms these big eruptions that we'll be talking about later, and provides a lot of the heat to the overlying hydrothermal system that's sitting between the magma chamber and the surface. So this hydrothermal system or geothermal system is mostly groundwater, meteoric-derived groundwater that's coming in beneath the subsurface, and it intercepts a lot of the signals that are coming from down below. So one of my goals as a scientist is to try and study that hydrothermal system and to try to see through it into what's happening down below. Okay, so I'm going to have a little drink, and we'll get into the details. So here's a map of Yellowstone. So we're in northwest Wyoming on the border with Montana and Idaho. And those are the state boundaries. The park boundary is blue, and here it's about 100 kilometers across, and each way it's 9,000 square kilometers total. Here is the roads through the park, these pink lines. You'll see them in many of the figures. And here are the 3 calderas that formed during 3 very large eruptions at Yellowstone. The first one is the 2.1 million year old Huckleberry Ridge Tuff and the caldera that formed during its eruption. The next one is 1.3 million years old, and this one here is the Yellowstone caldera, and it is from the eruption of the Lava Creek Tuff 640,000 years ago. So this one, Gail had mentioned the size of this eruption was 2,500 cubic kilometers. This one is about 1,000 cubic kilometers. And that is enough magma removed from the ground to get called a super eruption. If you're a volcano and you've had a super eruption, you get called a supervolcano. And so that's all the terminology you need on that stuff. Okay, so those big eruptions put out a lot of ash. And here are the basic areas that were covered in the U.S. as a result of that. In fact, we know where the ash went primarily through deposits that are found in the Ogallala Aquifer. Turns out that all of these locations were important marker beds for studies that began in the late 19th century. They were called the Perlet Ashes, but nobody actually knew what they were. Where they were from until a variety of guys, including Glenn Izett and Bob Christensen, who's here in the audience, started to work, and they were able to tie everything back to Yellowstone. So you can see there are a couple interesting things. First of all, there's some ashes that get out into the Russian-American River and are rather thick out here. In fact, even in the Gulf of Mexico and some of the submarine canyons, there are tens of meters of ash that came from Yellowstone. So a lot of what we find today is fluvial redistribution. The Mississippi and the Missouri, they had a lot of ash to move after those big eruptions, and so they end up down in the Gulf of Mexico. So we really didn't know or didn't have any feel for how much ash might have landed in different areas of the country as a result of a big eruption like this, because everything that we're finding is pretty much redeposited. Another strange thing about the distribution is that there's a lot of ash out here in California, and even a significant amount of non-fluvial distributed ash that's out in this deep sea drilling well. So one of our colleagues at the USGS, Larry Maston, has done some work on this. Larry's actually another Stanford grad. He got his PhD with Dave Pollard. And he, over the last few years, has been working on this ash modeling effort. It's called Ash 3D. And it's intended to be looking at where the ash will fall out as the result of various different eruptions in Alaska and Iceland and places like that. So it's a finite volume model. It's Eulerian in scope, so everything goes up into the air. You take a wind field data, and you see where the ash falls out as a result of a fairly complex fluid dynamic model. And so Larry started doing some experiments, some runs, model runs. Here, this is for a fairly small eruption, I think 10 cubic kilometers. It's just letting the ash fall out over a couple days. And no matter what Larry did on these early runs, pretty much all the ash, if it was a day run, a week run, a month run, or a 3-month run, most of the ash ended up east of Yellowstone. And so it wasn't until he started putting a new aspect into the model that he started getting different results. And that is, he started considering the possibility that there was an umbrella cloud in some of these really large volcanic eruptions. Something there really hadn't been a whole lot of modeling on before. And an umbrella cloud is when so much ash and so much heat are being added to the atmosphere that the ash moves well above the level of neutral buoyancy and then collapses back down. It does so in a radial pattern, and so ash can be transported against the wind, essentially creating its own wind. And as a result, the later model runs found more circular isopachs and extending much further west than in some of the earlier modeling attempts that were done. So that's just one little science tidbit that I wanted to put out there. So, but that's the big eruptions at Yellowstone. There's only been 2 of these super eruptions. There aren't very many of these big explosive eruptions, and it's very possible that Yellowstone will never again experience an explosive eruption, anything like the ones that have happened in the past. Most of these eruptions, most of these volcanoes, they live, they die, and maybe there will be a new volcano springing up further northeast of Yellowstone someday, and there will be more big eruptions. But we don't know for sure. What we do know is there's probably going to be more lava flows at Yellowstone. And here are some examples of what's come out of the ground just in the last 640,000 years since the last super eruption. And so each one of these little pink units and some of the orange units represent individual lava flows. The most recent one at Yellowstone is this one. It's the Pitchstone Plateau flow. It's about 70,000 years old, and it's probably big enough to cover all of Palo Alto and Mountain View and maybe a little bit more. They're fairly large. So these are occurring. There's maybe 30 or 40 of them in the last 600,000 years. So they're happening far more often on average. But again, Yellowstone's just stopped having volcanic eruptions about 70,000 years ago. And this is Bob Christensen. Again, he's right here today, and he's one of the legends of Yellowstone geology. He's the one who mapped all these lavas. He's the one who put together the program to date the ashes and track where they were and figure out how many of them there were. And so he provides a lot of what we're talking about in terms of our knowledge of Yellowstone geology. If you go to Yellowstone and you see the Grand Canyon of the Yellowstone, you're going to be looking at some of these post-caldera lava flows. This is the canyon flow and the Tuff of Sulphur Creek found right here. Also, during the last 600,000 years or so, there's quite a bit of these yellow units, basalts, that have been erupted at Yellowstone. And however, I mean, they've been also happening relatively commonly, but they are never found anywhere inside the caldera itself. And so this is one of the early pieces of evidence that they put together to realize that there was still molten material down there beneath the caldera, that basalts were being produced in the mantle. They were coming up, but they were denser than the rhyolite in the magma chamber higher up, so they weren't able to penetrate it. The silicic magma is very viscous as well, so the basalt would just pond below. Instead, outside the caldera, the crust is cooler, it's easier to fracture. The silicic magma is not there, and the basalts can penetrate and rise up to the surface. By the way, Chris is also a Stanford graduate, and his advisor was Bob Compton. Now, here we're going to talk a little bit about earthquakes and faults. These are all quaternary faults in the region. A lot of them are north-south trending, similar to the Basin and Range region that's surrounding the park. These ones head up through the Norris-Mammoth corridor. These ones go down to the Tetons. These go out towards Hebgen Lake. And then you also see a variety of faults inside the caldera. This is on what we call the Sour Creek Dome. This is the Mallard Lake Dome. And so these are the areas where the caldera is constantly moving up and down in these caldera uplift subsidence cycles. And so these faults essentially are accommodating the strain associated with the frequent continual uplift and subsidence of the caldera. So a lot of the geophysics of Yellowstone, a lot of the earthquakes that I'm going to show, and a lot of the slides are from another legend of Yellowstone, and that is Bob Smith. He's a professor at the University of Utah, been working there almost 50 years, and he's done a tremendous amount of work. He's supplied some of the supplies I'm going to show today. However, he's not a Stanford graduate, so no photo today. So now we're going to overlay some of the earthquakes and just show that there's earthquakes pretty much all over Yellowstone, all along these faults on the resurgent domes. And then in this area out from Norris Geyser Basin out towards the Hebgen Lake fault zone. It's possible that a lot of these earthquakes out here are still aftershocks continuing after the 1959 magnitude 7.3 earthquake that was out at Hebgen Lake. And here are some slides from that. Just some photos. Caused a big landslide. It buried a campground, and 28 people died as a result. It also created a lake called Quake Lake and caused all sorts of changes to the hydrothermal system 20, 30, 40 miles away in Yellowstone. So really an amazing event and sort of tying in the relationships between earthquakes and hydrothermal processes at Yellowstone. The last thing that I'm going to talk about here in terms of hazards, so we've worked from these maybe every 500,000 year big eruptions to 1 million years, to the lava flows that happen every 10 or 20,000 years, the earthquakes, big earthquakes maybe happening every 300 or 400 years, maybe a little bit less than that. And then we have these hydrothermal explosions that are found. And all of the stars on this plot represent hydrothermal explosions that are post-glacial. So they're all in about the last 15,000 years. And the largest of them is Mary Bay right here, which is 3 kilometers across. So it's 2 miles across, enormous hole in the ground. And these are not actually volcanic events in the sense that magma does not appear to be involved. These appear to be truly geothermal events. Here we have Indian Pond, that's one of them. It's about 4,000 years old, about 400 meters across. Here's the road going by and a couple cars and things. And in this case, you have a boiling groundwater table. It's boiling all down as pressure increases, and so it's always along the boiling point. So if you're able to destabilize the top of the system and decrease the pressure on the system, you'll find that the water is way above its boiling point, so you get flashing, you get phase transformation as water moves to steam. There's great volume expansion. It breaks the rock up. It throws it into the air. So this is something that has happened quite a few times in the last 10,000 years at Yellowstone. Is probably one of the bigger hazards to visitors coming to the park, but it still doesn't happen very often, although there are small hydrothermal explosions that are happening pretty much all the time. And so in this case, this is one at Biscuit Basin that was seen a few years ago. Okay, so now I've kind of gone through the major things that happen at Yellowstone in the past and how often they happen. Now we're going to talk about what's going on right now. So we're going to talk a little bit about some of the main things. I think I hit that button too many times. Deformation, earthquake swarms. So swarms represent when you don't have a big main shock aftershock sequence, but you have lots of earthquakes that are similar in magnitude with no really big earthquakes, and they generally happen in a single geographic area. And then we're going to talk about hydrothermal phenomena as well. So this is an INSAR image put together by Chuck Wicks, the USGS, and here's the caldera in the black outline here. So it's interferometric synthetic aperture radar. It's taken by a radar satellite that's out in space. It's looking down on the Earth, and in this case, it takes 2 pictures. One's in 2005, and 2007, compares those 2 images, and looks at how much the ground surface has moved up towards the satellite. In this case, you can look at them as sort of as contour lines. The maximum uplift is in the center here on the Sour Creek Dome and the Mallard Lake Dome, progressively decreasing outward and then actually moving to subsidence as you move out to this area at the northern part of the Yellowstone caldera. The yellow triangles are GPS stations, and in a second I'll show you data from those GPS stations. So this is, by the way, again, 2005 to 2007. You have the caldera rising, and it's happening. This is over a 2-year time period, this map. Now here are where we have GPS stations at Yellowstone. Both the red and the yellow triangles represent different GPS stations. So these are monuments. They're in the ground. And we can get time series, in this case at Old Faithful and at White Lake on the 2 different resurgent domes. They're the blue lines, and you can see they're rising during this period from 2004 out to 2010. Same with White Lake. And the displacement can be read here. The maximum displacement was about 25 to 28 centimeters in the Sour Creek Dome area. So something like that rising, if you add up the total volume increase of Yellowstone over those 6 or 7 years, it's on the order of 0.4 of a cubic kilometer. So a huge increase in the volume beneath Yellowstone. One of the neat things that happened is that the uplift ended right around the time of these earthquakes. So we have earthquakes down here, the number of earthquakes per month. You'll see a bunch more plots like this. Not much happening, and then at the end of 2008 and early 2009, there was a big swarm beneath Yellowstone Lake, and then there was another swarm out here beneath the Madison Plateau, and by the time that one was over, uplift had ceased, and a period of subsidence had begun in the caldera. This is something that had been noticed in the past. Back in 1985, there was a big earthquake swarm out in the western part of the caldera, and that was the time that noticed again by the University of Utah folks that the caldera stopped rising and started to subside. So interesting correlation. So here's a map of the two swarms. This one here at the north end of Yellowstone Lake, this one out here in the Madison Plateau. And the next slides I'm going to show a little bit more about this Yellowstone Lake swarm and then this one out here. So this lake, this particular swarm had everybody pretty tense, I'd say. I had most of the scientists tense. A lot of people were on holiday. It was between Christmas and New Year. Anytime you have earthquakes going on beneath a lake, it freaks people out. Just things happening beneath lakes, not good. People, they want you going down there, right in the ice-covered lake. Break through that thing, send your ROVs down there, get in and see what's going on. But we didn't do that, and it did end. These are seismograms from the 27th. These are two different seismograms, LKWY and YTP. They're both near Yellowstone Lake. Each line represents 15 minutes. They change color as you move through time. And each one of these little lines represents a separate earthquake. So little earthquakes here, they get bigger. Here's a 2, there's a 3.5. This is the largest one of the entire sequence, was a magnitude 4. Jamie Farrell, who was a PhD student and did a lot of work at University of Utah on this particular swarm. So very intense earthquake activity going on, about 900 located earthquakes in the end from this swarm. And here's a couple interesting diagrams. Date of the earthquake is shown here. They start out blue and they get more yellow and green as time goes on. So you can see that the blue ones are early on. It starts to the south. The earthquakes are migrating to the north over time. Also, you can see that the biggest earthquake was the deepest one. This is a cross section. And that the deep earthquakes pretty much peter out as time goes on, and you only get shallow earthquakes towards the end. Jamie's model for how this worked is that there was some sort of fluid input, perhaps magma, perhaps some sort of a magmatic burst. There was a somewhat explosive source for the largest earthquake, the magnitude 4, that's consistent with intrusion of fluid. And then you might have some sort of a movement of the fluid or a pressure pulse that's moving along a pre-existing fracture zone and migrating to the north over the next 2 weeks. The next swarm, again, is out here, and you can see it kind of looks like a blob on this particular diagram. We can fix that, though, by doing various different waveform detection and relocation. This work that I'm about to show is by another Stanford grad. Oh, wrong one. So David Shelley is the wrong talk I had there. David Shelley was also, he's a Greg Barroza student, and he works at the USGS in Menlo Park, and he's got all sorts of fancy techniques for doing a waveform-based detection. So we can look at that seismogram, and you can train the software to detect everything that's in an earthquake, and therefore you're not relying on the broad seismic network to individually locate earthquakes. You can kind of say, these are all earthquakes. So you can get about 3 or 4 times more events, and you can do all sorts of relative location, double difference techniques to put them and get better relative locations for the earthquakes. So that's what he did, and so this is a little movie that shows how that works. Let's see, I think I have to go over here on this case. if I can. Is that going to show me? There we go. So one thing that you can see here is that everything collapses now on a single dipping, a 55-degree dipping plane that is most likely a pre-existing fault of some sort, active fault. And it's been, and if we stop everything now, we can just turn the earthquakes on and let them go. And you see there's little flashes and bursts of earthquake happening along this plane beneath the Earth. They're migrating with time. Some of the later ones are in these little groups way out on the periphery. And again, there were no clear evidence for any deep intrusion of magmatic fluid of any kind, but there's clear evidence that, well, David's model, again, is that there is pressurized fluid along this fracture zone. It gets tweaked by some sort of process deep down, and then pressure is transferred along other parts of that pressurized surface to cause all sorts of triggered earthquakes along the plane. And so, again, these two swarms of earthquakes were what was needed, evidently, to stop all the deformation that had been going on over the last 6 years and move the caldera into a period of subsidence. It's pretty neat stuff. Most of the latest activity has been taking place at the Norris Geyser Basin and to the north of the caldera. And so this is, again, a map of the area north of the caldera. So this is Norris Junction in here. Again, we're looking at a period now between October of 2013 and June of 2014. And again, the epicenters are color-coded. So each of these different groups, they're slightly different times. The yellow is different time, the blue is different time. And so you can see that seismicity is hopping around on all of these various different north-south trending zones. And none of these were actually relocated. These are all the original locations from the University of Utah network. So over a 7-month period, much more intense activity than we'd seen before. Lots of different fault zones being reactivated. Here's an actual histogram then for the area north of the caldera, showing the period from 2001 out to not quite the present day. And you can see there was a lot of earthquakes back in this period, and this is when that area had previously been under an uplift, period of uplift. That stopped around in here when the caldera started rising, and so there were no earthquakes actually either to the north or in the caldera for a very long period. Then those big swarms in the caldera happened in here and in here. But in this area up here, nothing was happening until this last period starting in mid to late 2013. So this is a nice diagram that summarizes both the earthquakes, again, down below, with the GPS data. And this is put together by the deputy scientist in charge of YVO, Peter Cervelli, Paul Siegel's student. And so you can look here, and the green, yellow, orange, and purple lines are all GPS stations within the caldera. So all this period of uplift coming through until 2009, 2010, and then going back down. But here's the Norris area to the north of the caldera, slow subsidence, and then all of a sudden we start this rapid ascent at the time we're getting all of these earthquakes. The rapid ascent was actually about 1 centimeter a month in that area. And then in March 30, 2014, we got a magnitude 4.8 earthquake. Norris immediately starts to go down. It's as if there was some bladder down there, somebody poked it with a pin, and it started slowly losing air. The entire area started moving back down, but you'll notice the caldera started rising again. It's crazy stuff. There's a lot of smart people trying to figure out exactly how the caldera and the area to the north are related, how you can just start crustal deformation that quickly, how it's related with fluid flow in the crust versus the deformation versus the earthquakes. I'm not going to try to give you any answers today, but there's a lot of cool stuff going on. Okay. We've mentioned how fluid flow and earthquakes may go together. We actually have some hard evidence for that, and that's from my colleague Bill Evans over at the USGS. He did a study at the mud volcano area, and he also looked at other places at Yellowstone, and he looked at tree cores. And what he did is he took individual rings and he sent them out to Livermore Lab, and he looked at the carbon-14 in the individual tree rings. So there's a big swarm in 1978 at Mud Volcano, at a place within Mud Volcano called Cooking Hillside. And so in any of these individual rings, well, let's take a tree that's growing here in California. Pretty much all the CO2 that's going to be taken in by that tree is atmospheric carbon dioxide. It's going to be the stuff. And it's all going to be normal carbon dioxide. It's going to be the stuff. It's got a decent amount of carbon-14 because there's lots of cosmic rays coming down. Those cosmic rays are hitting nitrogen atoms. They're generating carbon-14. And so you'll see a normal amount of carbon-14 in all the tree rings. And it wouldn't change if we were to look at all the tree rings in a tree out here. In Yellowstone, we have two different sources of carbon. We have the carbon that's in the air, and we have the carbon that's coming up through the ground. And that carbon doesn't have any carbon-14 in it. It's carbon dead. So we can do an easy mass balance by looking at the different tree rings, and we can say, okay, let's say normal times a tree ring has about 25 parts per million dead carbon, which would mean that it's about 1/16 dead carbon and 15/16 atmospheric carbon. But at Mud Volcano, the year of the swarm, there was a 40% increase in dead carbon. And the following year, 1979, there was about a fourfold increase. And that's consistent with about a fourfold increase in flux in the area near this particular tree. So a huge amount of increase in gas discharge from the ground, and that this tree is growing from, but apparently not getting injured enough. It kept growing, and it's still growing today. And then it gradually went down and returned to normal. So in this case, we have some evidence that maybe the CO2 actually occurred and was seen early enough that maybe the CO2 actually had something to do in generating the swarm of earthquakes. But it's also possible that just the fractures that are opening up in the ground allowed very rapid transport and increase in CO2 to get out to the surface. Okay, so we've now given a little introduction into gas, and so what I want to do right now is I'm going to talk a little bit about the stuff that I get nerdy about, and that I think is maybe a different perspective on all this geophysical stuff in thinking about Yellowstone. So we're going to talk a little bit about the lessons that we can learn from the gas that comes out of Yellowstone. The first thing I want to say, I have a couple little seeds to plant, and the first one is that Yellowstone is really big. And so it works a little bit differently than most other geothermal areas that you might go to on Earth. This is the geysers right here. Okay, this is the geysers right here. It's in Northern California. It's to the north of us here. It's one of the largest producing geothermal power plants in the world. It's a steam field, and it's about 1,000 megawatts of energy production. But if you take the entire outline of the geysers, it fits right there within Yellowstone's caldera. And of course, there are thermal areas pretty much all over Yellowstone. So in a way, we could think of each of these thermal areas as being somewhat distinct in character. Most geothermal areas, most of the models we have for how geothermal systems work are based on relatively small areas and looking at how the fluids differ in chemistry that are all within a few miles of each other. So again, here, now Yellowstone, we got this big picture system where the thermal areas could be 30 or 40 miles across. The next little thing I want to mention is that a typical model for a hydrothermal system is you've got magma down below, you've got heat coming up, and that is heating this hydrothermal system that is somehow there, and it just exists. And so then we can see how that hydrothermal system varies by doing things to it or allowing things to boil off of it, for example. And then we see the springs, maybe where the geysers are, where the neutral waters are coming out. And then up high, we might get some fumaroles where the steam and gas is rising. On a volcano, we often think about things a little bit differently in that we normally think about the gas coming straight off of the magma. So at Yellowstone, we've always kind of thought of it as a geothermal area, but we also know it's a volcano. So how much of this material is actually coming off of the magma and is affecting the hydrothermal system in the way that we might think about how it operates? Okay, so the first thing we need to talk about is carbon dioxide, because it's kind of the main thing going on at Yellowstone. There's a huge amount of CO2 coming out of the ground at Yellowstone. Cindy Werner and Sue Brantley estimated about 45,000 tons per day coming out. That we really don't have any better estimate at this point in time. that makes it one of the biggest CO2 fluxes on Earth. It's one of the volcanoes with more CO2 coming out than any other. Etna and Kilauea are the two others that are most similar. And we can also see through isotopes, I'll show you in a moment, that more than half of that CO2 that's coming out of Yellowstone is mantle-derived. And because it's mantle-derived, we can tie it to the basalt. And if we know how much gas is likely to be dissolved in basalt coming off of the mantle, then we can say that on the order of several tenths of a cubic kilometer of basalt are coming into the crust and degassing every year and providing CO2 that comes out towards the surface. So essentially, Yellowstone is Kilauea beneath Wyoming. It's really not any more complicated than that. Well, it is more complicated than that, but it's a lot like that. Here's a little bit of the data just showing you this mantle CO2 presence. This down here on the x-axis is carbon isotopes. So delta C13, it's the carbon 13 to 12 ratio relative to a standard. And just focused right here, this yellow box is mantle diamonds. Morb sits right here. Here's a bunch of notable mafic volcanoes on Earth. And the Yellowstone samples all fit in this green ellipse. This is the CO2 to helium-3 ratio. Helium-3 pretty much is only coming from the mantle, so you're not going to see very much of it coming out of the crust. And therefore, the CO2 to helium-3 ratio is really high. If you're taking sediments and you're degassing them, or you're taking limestone or some other source and you're turning it into CO2. So limestone and sediment are going to have orders of magnitude higher CO2 over helium-3. Yellowstone samples are consistent with at least half of the CO2 coming from the mantle. All of the data that I'm showing are based on the work that we've done over the past 12, 13 years. I work with Deb Bergfeld in Menlo Park, and we've collected a lot of these samples together. We've gone to over 100 different places. We probably have 100 more places that we could go that we haven't been to yet, and about 160 analyses. And we collect them in Giggenbach bottles. They're little glass bottles. They're filled often with sodium hydroxide solution. And so you can collect lots and lots of CO2 and condense it into the caustic. It allows you to collect more gas. And so we get all of the major and trace gases that are coming out of the ground. And then we do the isotopes of carbon and sulfur and hydrogen and deuterium, and then all of the noble gases as well. And yeah, so we have lots of data. And in general, we try to focus on fumaroles. Now, fumaroles are above or at the boiling temperature of water. So we're not just sampling gas that's coming through a pool. And so with a fumarole, you're getting mostly steam, and you're getting some gas. The gas at Yellowstone is generally 95% carbon dioxide. Everything else is minor compared to the CO2. But it's there, and it's useful and interesting. But mainly, we're getting steam, and we're getting CO2 in these fumaroles. So this next plot, I think, is actually really interesting, but it takes a second to look at. So here we've got percent gas, or log percent gas, down on the x-axis. So in here, 1 means that we have 10% gas. 10% gas, 10% CO2, 10% gas, 90% steam. Here, 1% gas, 99% steam, 0.1% gas, 99.9% steam. So we're going from gas-rich to steam-rich as we move over in this diagram. And on the y-axis, we have nitrogen over CO2. CO2, as we said, is coming from depth. Where does nitrogen come from? It comes from the air, or more specifically, it comes from air-saturated water. So groundwater is coming into the system and it's bringing nitrogen. So we have what I think is a rather beautiful correlation between the amount of gas that's in the system and the amount of so basically, the amount of water and atmosphere-related gases are tied together. So meteoric water is coming into the system, it degasses, it gives you nitrogen, and it gives you argon. These symbols are getting bigger as you move, as they get higher and higher argon to helium. Again, helium is a deep gas, argon is coming from air in air-saturated water. So we've got this trend that stems from a deep magmatic component. In fact, these blue dots are mud volcano. And mud volcano is the most mantle-like helium isotope signature in the park. These are the most gas-rich samples in the park. And then we're coming in and we're getting more and more water, more and more steam, more and more argon or nitrogen. Now, Okay, so what, you say? Well, what's kind of interesting about this is that typical models for how geothermal systems work usually rely on the concept of boiling. And when you boil groundwater, or any kind of geothermal water, well, you lose gas. So you're going to progressively lose gas. And you're also going to progressively lose the gases that are most insoluble first, and the stuff that's soluble, like CO2, you're going to hold on to. So these are the sorts of trends that you expect if boiling is somehow controlling what you see at Yellowstone. But you don't see anything like that. So I think actually that if you look at the big picture in Yellowstone, something very different is going on. So a normal geothermal system, again, we're looking at this. There's just this hydrothermal system. It exists, and you boil it, and you should get a trend of changing liquid composition and changing steam over time. But if it looks more like this, and you have this constant gas coming off of depth, some areas you got lots of groundwater, and some areas you don't have much groundwater at all. But you have lots of heat at Yellowstone. You got this enormous mantle flux of heat coming in constantly, and so it can boil any water that's there. It's got the heat potential. The rocks are already at their boiling point, and so some areas you're seeing a lot of gas and not very much steam, and some areas you're drowning everything in this meteoric signature of argon and nitrogen and water. So that's little lesson one. The next lesson is just a one-slide lesson, or a summary, and that is that hydrothermal fluids, and this is dead obvious to some people, not obvious to others, but they're mixtures, okay? So if we look at any particular gas species or any particular isotope, and we do a study on that, we're going to learn something. But if you study another isotope or another gas species, you're going to learn something completely different. And that's because they're not all coming from the same place. They can all come from different places and wind up in the same place, and then you sample them. And that's the same thing with magmas, too. If you study strontium isotopes, neodymium isotopes, osmium isotopes, you might learn different things from each one. You can't really learn anything generic by studying one isotopic system. So Yellowstone, the water, and a lot of the heavy noble gases and the nitrogen argon are coming from meteoric fluid that's recharging into the subsurface. But CO2 and H2S are coming from the magma. Methane is coming from all sorts of crustal rocks. They have all sorts of organic materials, and in the eastern part of Yellowstone, there's little oil factories down there that are producing all sorts of organic gases. And then helium is another interesting story, and it can be magmatic, and it can also be very crustal. And so the last little piece of my talk here is a little story about helium that we recently worked on. And so I'm going to talk about that. I guess as a precursor to saying that is the reason, that one of the things we're trying to look at is just how open is the crust, how much do things change over time, how easy is it for gas to flow through the crust. And this is something that we grapple with. Our groundwater ages, our geochronology depends on kind of knowing how fast things can move. And so this lesson from Yellowstone is something that comes out of the work that we're doing, but is applicable actually fairly broadly. And it starts from this diagram. Okay, so RC over RA is the helium 3-to-4 ratio of the sample compared with air. And the mantle signature at Yellowstone is maybe 16 or 17. We get maximum values. It's possible that the mantle is actually somewhere up here, and that mud volcano is just already mixed with mantle and other materials. But as you see, as we move down and down on this plot, and lower mantle signature, or lower and lower R over RA, we start getting higher and higher helium concentrations. And that makes sense because the crust has no helium-3 to speak of. But helium-4 is constantly being generated. The crust generates helium-4 because there's uranium and thorium in the crust. Uranium and thorium are breaking down, they're radioactive, they produce alpha particles. Those alpha particles are helium-4. So if you have really uranium-rich crust, you'll produce more than if you have uranium-poor crust. If you have old crust and you're able to hold on to that helium, you'll have more helium-4 than you would if it were young crust and with the same concentrations. So we notice here that we have this location at Yellowstone that has a very mantle-like signature, and then we have this location out here, Heart Lake Geyser Basin, where we have high helium concentrations. It's not actually a very gassy area. It's mostly a steam-rich area. But of the gas that comes out, it's fairly rich in helium, and it's very low in R over RA. The crust, the R over RA of true, just no mantle crust, should be on the order of 0.01. So basically very, very little of the helium-3. So we went to Heart Lake Geyser Basin, and as with every place that we work at Yellowstone, we try and analyze and try and do we measure the diffuse gas flux with accumulation chambers. So we basically do grids over the ground to try and estimate how much CO2 is coming out of the soil. And when we do that, we can come up with a flux of carbon dioxide in tons per day. And we've done that many, many places now, and we're still trying to do more. If anybody wants to do some, let us know. We also sample the fumaroles so we can get CO2 to helium ratio. And then we're sampling the helium isotopes. Here's just the map of the helium isotopes in the park with some of these high areas, Heart Lake Geyser Basin with the yellow and green down here. We take the highest R over RA for the Heart Lake Geyser Basin, and then we can calculate the helium that's coming from the mantle and the helium that's coming from the crust. And the helium that's coming from the crust is 5,000 moles per year from this one geyser basin. Okay, well, that doesn't mean anything to anybody, but what we can do to make it mean something perhaps is we can come up with this number for how much comes out of the crust beneath Yellowstone in a year. How much helium-4 do we generate in a year? So let's take 9,000 square kilometers for the park, 43 kilometers depth down to the mantle, and then we assume normal uranium and thorium concentrations for the crust. And we calculate how many helium atoms are generated in a given year. And Heart Lake Geyser Basin produces 35% of what all of Yellowstone can produce in a year, the crust beneath Yellowstone. It's a lot. How does that happen? You know, you're generating it all and sending it out in one place? It doesn't make sense. Well, we can take 4 areas in particular that we've worked at, and we can calculate 21 times the whole crust generation just for those 4 thermal areas. And those are 4. There are 4 outside the caldera. They tend to have the lower R over RA, so they're having, you know, they're robust at producing that crustal helium. We tried to estimate an entire park degassing. That involves more assumptions than this particular exercise, but our best estimate for Yellowstone is around 600 times the helium flux. 600 times more than you can generate in a year is actually coming out of the park right now. So if you consider that Yellowstone's been active for 2 million years, and you add all that up, that means that about 1 billion years worth of helium has come out since the birth of this volcano. So what's going on? Well, Yellowstone is built on Archean rocks, okay? Pretty much everything down there, once you get below about 4 or 5, maybe 7 or 8 kilometers, is going to be Archean basement. That crust has been undisturbed. It's about 3 billion years old, but it's been undisturbed for 2 billion years. There's been no metamorphism, minimal fracturing, minimal earthquakes. There's no hydrothermal alteration. There were no groundwater hydrothermal systems. That area was moribund. It was dead craton. And so helium doesn't get out. It doesn't get out a cold, untectonized crust. People have speculated about this. There are papers on this in the literature, but it's always been a little bit controversial exactly how closed the crust can be to something as small and presumably fugitive as helium. But it definitely appears, based on this data set and lots of others, that diffusion isn't really going to happen unless there's significant gradients or there's advection. There's something to move the helium and break up the crust. So the region around Yellowstone was closed for 2 billion years to helium flux. And then the hotspot comes in and it starts hitting the Yellowstone region. It heats the crust. It melts the crust. It's metamorphosing the crust. It's fracturing. There's all sorts of earthquakes constantly at the place. And then there's 45,000 tons per day of carbon dioxide that's streaming through and picking up gas and bringing it towards the surface. So we have in one place, we have an evidence for how tight the crust can be and how little helium can move on geological timescales. And so how you could build it up in crust and have reservoirs of this gas that affects how we date our groundwater, or how we judge how we can fill a petroleum reservoir or natural gas reservoir, because helium is an important part of that modeling. And then we can break that up and we can send it all out in a geological, very short period of time. So the way I kind of view things is, actually I I should cut my hydrothermal system like I did in that other slide. We have variable amount of water in the crust. We have gas coming from the magma. We have gas coming from old crust. We have gas coming from young crust. We have gas coming up from the meteoric system. And it's all meeting and doing a dance down there in the hydrothermal system. And then we come and collect everything at the surface. So that's it. I have some sort of take-home messages in that if you learn anything, you learn that there's a lot going on at Yellowstone. It's Kilauea beneath Wyoming, and there's continual intrusion of basalt. There's a lot of unrest. It's on a low level, and it's probably been going on like this for 70,000 years since the last eruption. We don't really know that it has ever not been active like this. So we've got these swarms of earthquakes, deformation, and gas discharge. They're all linked in some way, but we're still fairly early on in our understanding of how it all works. And the geothermal system itself is a rather open system in that it's invaded by all sorts of different materials coming in from different places. At first glance, it looks like water that comes in from meteoric recharge, and it just reacts with the rhyolite. But the gases that are coming through are telling us a different story. All right, thanks.
Do you have any questions from the audience? Yes.
Jake, so you
Sandra.
a lot of evidence.
You like those pictures from? You were still here in those.
So you presented a lot of evidence for magma at depth and basaltic intrusions at depth and so forth, and that's going to influence the heat flow. But I mean, it's not like that image you showed with this big blob of magma at depth where it all just sort of comes up at once. It's presumably coming up, in a spatially complicated
Yes.
pattern. Is there any data on heat flow across the area through time? And could that have anything to do with, say, the uplift subsidence patterns and other things you mentioned?
So the only way that we can estimate heat flow right now, we actually have a good way of doing it. We're starting to be able to do it with satellites, but that's still kind of young in being able to do it. We use something called the chloride flux monitoring system. So we measure basically all of the chloride that's coming out of the hydrothermal system. This was first done by I guess it was first done in New Zealand by Bob Fournier. Some of you might know him, another legend of Yellowstone. He basically said, well, that hydrothermal system is all more or less starting out with a certain concentration of chlorine. So if we can measure the amount of chlorine coming out, we can measure the amount of hydrothermal fluid that's coming out in a year. And we know the enthalpy because we have a model for how hot that was. So we can basically say how much heat is coming out. So we have 30 or 40 years of heat flow estimates for our chloride flux. The problem is that the water that comes out of Yellowstone doesn't appear to come out in a way that relates easily to the uplift subsidence cycle. It relates more to how much did it rain that year, what's the infiltration, and how much hydrothermal fluid are we going to push back out. And so we see very little change with time. So the chloride flux is a really useful way to get out changes in the hydrothermal system and heat flow maybe over hundreds or thousands of year time scale, but not a very good way to do it if we're trying to understand, how much basalt came in last year. But I don't know, there's so much thermal inertia in the crust. There's so many different fluids that can absorb the heat. It's a very daunting task to try and link the heat flow to the uplift subsidence cycles. But
Well, forget about the heat flow then. Just the idea that presumably the basaltic magma is coming from depth, in a sort of haphazard fashion. Could that have anything to do with some of these patterns that you talked about?
well, for example,
Where there's uplift or
yeah,
where there's
absolutely. why is the northern part of the caldera rising and not the caldera? Is there, I mean, one thing that's crossed our mind is there some sort of a little switch or, that allows the magma that's coming up to go north or to go south and therefore push different areas. The problem is that the magmas that come out to the north typically don't look that much like the magma to the south. So unless things have changed since the last eruption, that's certainly possible, then we second guess ourselves about that possibility. But it could be magmatic. There are models that everything is.
I'm thinking of magma that doesn't actually.
Yeah, yeah. When you do the simple geodetic modeling, most of the sources of deformation come out as shallow as 5 kilometers and as deep as 10 or 12 kilometers. So there's plenty of options, and again, we're just kind of getting there. Yeah.
You mentioned that the supervolcanoes had been sort of sensationalized in the media, but it was 2.1 million years ago when this first eruption occurred. So it doesn't seem like the hotspot is going to be moving and relieving the pool of magma underneath. What's the bottom line with regard to the supervolcano risk?
The bottom line is it's out there in the realm of possibilities that it could do it again. But it's also so if you think about it, the system starts up and it generates rhyolite partly by crystallizing basalt and partly by melting crust and so eventually you're going to run out of new crust to melt. And I mean, this is Catherine and Ilya's model, is that you end up eventually kind of sucking fertile crust dry and you end up, your magma dies off. And the question is Yellowstone really done its thing in terms of producing these, or is it still possibly going to put something out? And is it going to put something out that's really big, or is it just going to find a little bit of the rhyolite to come out as a lava flow at some point in time? Or are we ready for the basalts to start coming up, rising through the caldera, burying everything, and then we'll start planting potatoes there, and it'll be part of the Snake River Plain. So, that's the long-term view. But, yeah, there's a lot more that's probably going to happen, but we don't know. Again, it's stopped 70,000 years ago.
So is there evidence that it's done that on the older caldera systems, that it sort of used up all the silicate material to produce siliceous eruptions and then migrate into more basaltic behavior? Is that
Yeah, well, if you're looking back along the Snake River Plain, that's exactly what happens. So all of those calderas died, the plate moved on, and it found new crust, new Archean crust or new crust to start to melt. And so as the plate moved, there was constantly.
The question is, did they stop producing silicic lavas before the source of heat moved away? So you sort of implied that it used up the material, the heat was still there.
Well, I guess my view would be that there would still continue to be silicic eruptions until there really wasn't enough heat anymore. But the question would be, how big are those silicic eruptions going to be? Can we generate 1,000 cubic kilometers in one hot liquid system? And what are the conditions that we need to do that in terms of kind of where you are in the life history of one of these caldera systems? Everything is possible. It's possible it could have another big one, just based on the other calderas down the line. How many big ones at Heisey? Yeah, 4. So there's precedence.
You mentioned these lake eruptions, and you mentioned that there have been a big number of them since the last glacial maximum, which got me thinking. I assume that means that they maybe were eroded by glaciers in the last glacial maximum, so you just don't see that many before that.
Correct.
But just more generally, though, so if there were glaciers there, what did the LGM look like at Yellowstone? Are there signs of subglacial eruptions? And if the hydrothermal system is so closely related to meteoric rainfall, what does that look like with a lot of ice around and maybe more precip during that time?
Well, there are, I guess what I can say is that there is a lot of evidence for hydrothermally altered glacial sediments in certain areas at Yellowstone. So there are these came deposits that are full of zeolites and other minerals. So there was a lot of basically glacial sediments that are being deposited and are being hydrothermally altered. So glacial hydrothermal activities certainly did not shut off. Another thing that we know is from, again, the work of Bob Fournier is that when we went down into the drill holes, the fluid inclusion temperatures were hotter than the current day temperatures. And so we got all that ice on top, the pressure increases, so the temperature of the water, the boiling temperature of water increases. So one of the reasons perhaps that when the glacial period ended and we removed all of that removed all of that ice, is that then we had a lot of superheat in the subsurface, and that caused some of these hydrothermal explosions. Not everybody agrees with that, but I think that was the original. What do you think? Yeah. Chris shakes his head. Yeah, and so that's an easy thing to speculate. But I don't know how much we really know about what happened at Yellowstone hydrothermally during the last glacial period. We know when the eruptions have occurred. And Chris could tell you, ask Chris after the talk, he'll tell you all sorts of stuff about what he's observed by looking at the sort of synglacial volcanic deposits.
Yes. One last question.
Have you been able to measure CO2 in fluid inclusions? And if so, has there been a variation in time with CO2 in previous hydrothermal systems versus now?
First answer, no. So I guess the second answer is moot. But yeah, you'd have to have a way of dating the various hydrothermal systems so you could make that inference. And so that's another whole thing of is trying to date old hydrothermal deposits and know what they are. But yeah, that would be a lot of work, and no, I haven't done it.
Well, thank you for that comprehensive talk, and let's thank Jim. I should have added that we have a reception afterwards with wine, beverages, and as well. Please join us if you have any more questions.
Where is the sunset?